In the last week, we studied binomial and negative binomial distributions, which were discrete probability distribution. This week, we study normal distribution, which is continuous probability distribution. Normal distribution forms one of the most popular and important concept in statistics, and you will find mention of normal distribution everywhere in statistics. This is one of the most important distributions in statistics. And for this reason, you'll see most of the calculations which mention a normal distribution. Most of the times, the data that you're dealing with is assumed to be having normal distribution. And in cases where it is known that the data is not following normal distributions, transformations can be applied to convert into a form which is similar to normal distribution so that the rest of the calculations can be easy and straightforward. The probability plot for a normal distribution is called the normal curve. We have seen it already. It looks like this. It's also known as the bell shape because it looks like an inverted bell. And you can see a line of symmetry in the center. And we are now going to have a look at the different aspects of normal distribution. Here you see a plot with the mean mentioned in the center. So now you see the line in the center, which kind of split this plot into two halves, equal halves. And why we call it line of symmetry is that if you draw it on a piece of paper and you fold this paper upon this line of symmetry, both sides of the plot are going to overlap exactly on each other. And then we see the mean mentioned, and another quantity that is mentioned here is sigma. The normal curve is bell-shaped and symmetric about the mean. This we have seen. And another important factor is, in this distribution, in the bell-shaped plot, the mean, median, and mode are equal. They coincide. So this distribution, the data which is following this distribution will have same value for the mean, same for the median, and exactly same for the mode. The total area under this curve that you see in front of you is equal to 1, because this is the probability of all the different values that a random variable which is following normal distribution can assume. So if you look at this x-axis, this plot, with whatever area it covers, this total area is 1, because at any given a range between 2 points here on the x-axis, whatever falls under the plot is basically the probability of x, or the random variable, assuming those values. Another important thing in case of continuous distributions is that we cannot find the probability for a given or one value of x, because the continuous distributions, they're always defined as ranges of values. We've seen that already. The random variable, which is continuous in nature, we always define the probability as a range of value for which probability is computed. The normal curve approaches but never touches the x-axis as it extends farther and farther away from the mean. So here, it might seem to be touching the x-axis, but it never does that. So which means the probability becomes lower and lower and lower, very small, but it never becomes 0. And yet the area under this curve, the entire curve, including the extended left and right tails, is 1. And it is defined by a function. Between the mu minus sigma, sigma is the standard deviation, and mu plus sigma, which you can see here, in the center of the curve, the graph curves downwards. The graph curves upward to the left of mu minus sigma, to the left of this mu minus sigma, and to the right of mu plus sigma. The points at which the graph changes from curving downwards, upwards to curving downwards, are known as the inflection points. So you see those points here. You see that the plot here seems to be straightening up in a sharp upward slope. So the point at which this happens, the curve here, this curve seems to be kind of straightening up. So as if someone pulled this curve up at this point and it was being pulled down at this point. Similarly, here you can see the curve was it's being pulled down towards the x-axis, and here it's kind of straightened up or being pulled up. So the points at which this happens, where the graph changes from curving upwards to curving downwards, they're known as inflection points. And the use of these inflection points are in cases where you do not know the standard deviation for the distribution. There you can, and if you just have the graph and you don't have the values, these points basically represent one standard deviation away from the mean. Towards the lower values, it is one standard deviation minus the mean at this point towards in the left half, and it is one standard deviation plus the mean on the left on the right half. And this acts as the random variable for which the values are being plotted. Once again, the values are always mentioned as ranges when your this random variable is a continuous random variable. Now, here you see the density function of normal distribution, the probability density function, or the PDF. Earlier, we have seen the PDMs of binomial distribution and negative binomial. And we've used those functions to calculate the probabilities of a certain value of random variable. Here we know that we cannot have one point at which we can compute the value of probability. The reason is that we're going to see in detail why this happens, but the continuous continuous random variables, they're always specified as intervals. So here you see a function which calculates the probability of x, which is a certain range of values for the random variable, which is continuous for the normal distribution. Now, it might seem intimidating, but again, there is a good news, which is that we'll never ever be using this function to calculate the probabilities. And the reason for this is, here you can see some values which are constants, which are there, which you know already, and they're constants, such as pi, such as this exponential 1 by 2. And there's some that one, and there's some values which are variable, which can vary. Here you can see sigma, which can be different for every data for which we're calculating, constructing this distribution plot, and mu, which is the mean of the data for which we're constructing this plot. X is basically kind of an input, because you put x into this function to get a value out, which is the probability of x having this value. Now, what happens when we have different values of sigma and mu? We get different probability distributions. The shape is going to be the same. It is going to be to look like an inverted bell, but the only difference would be the span on the x-axis here at the bottom, and the how sharp the peak is, how high the peak is. So you see, and another thing, of course, where on the graph, on the number line is it located. So you see here, this distribution seems to be having higher values because it is towards the right on the number line, and it ranges on values from 11 to 17. Whereas this black distribution is very similar to green, but it has a range of values from 7 to 13. And of course, as we said earlier, this tail might be extending up till towards the infinity, but the probability of values in that range would be very small, very rare, very close to zero. Then you see the red distribution, which is shallow, which has a wider base. It spans over a large number of values, but the peak is not as sharp as the other two. So the two parameters that make difference, that influence how your distribution would look like. In addition, of course, each one of them is going to look like an inverted bell, but what exactly the height of this plot would be, how pointed the tip would be, how wider the base would be, is determined by two parameters, which are the parameters for normal distribution, and those are sigma and mu. We saw in case of binomial distribution that there were also two parameters, which was the number of trials and the probability of success. And similarly, with every distribution, most of them, we do have certain parameters which characterize the distribution. The normal distribution PDF has two parameters, which we have seen. And if a variable follows normal distribution, we write it like this. So we need to specify two parameters, mean and the standard deviation or sigma. Now, coming back here, I told you that this is good news that we never use this intimidating function to calculate the probability of a certain range of values for x. But then how do we do it? We do it using some already pre-calculated values, and all we have to do is to find the desired value. And for that, we need to study one more distribution, which is an equivalent of normal distribution, and it is the standard normal distribution. We also know it as the z distribution. And here it is. It is exactly equal to the normal distribution, except for the mean always is 0, and the standard deviation always is -1. And as I said earlier, the data which is known not to be following normal distribution, we can apply certain transformations in order to convert it into normal distribution. But data which is already following a normal distribution can very easily be converted into the standard normal, where the mean is kind of fixed onto 0, and according to that, the standard deviation is also recomputed to be equal to 1. So the special normal distribution with mu equal to 0 and sigma equal to 1. Any normal distribution can be transformed into standard normal. Once done, we use the standard normal tables to find it. So for the reason that we do not have to compute that complex function to find the probability values is this. We convert our distribution from the data that we have, which might have any value of the mean, any value of the standard deviation. We apply certain transformations and convert it into standard normal. And then there are standard normal distribution tables which are already computed, already there. We simply look up the values that we need to find the probability. So it's just reduced to the calculation of that function is reduced to looking up values in the table, which is much easier than that. And how to do is that for every each value or range of the random variable for which we need to find the probability of, we need to find the z-scores. And the expression for that is very straightforward, which you see here. So if you want to calculate the probability for x equal to x, and when I say x in case of continuous random variable, it always would mean some range. It would mean x is greater than certain value, or x is less than some value, or x is between two values. It always is going to be in interval. Mark this, I repeat it again, whenever we are looking up values or whenever we are computing probabilities for a continuous variable, a continuous random variable, we always do that over ranges. Then this is how we compute it. So if you have certain values of x and you need to compute the probability, first, we need to convert those values. Basically, when we talk of intervals, we have the endpoints. So if I say that x is greater than equal to, say, 30, so I have this endpoint or a reference point 30, and I need to know the probability of x having values which is less than 30, or maybe x having values which is greater than 30. Or it could be that I want to find out the values of x which are between 30 and 60. So in that case, I'm going to have two endpoints, 30 and 60. So it will be range for which you are going to compute the probability of, but you use the reference or endpoints to find the z-scores. So here it is done by this expression, which is x, the endpoint that you're considering, minus the mean of the population that you're studying the data, and divided by the standard deviation. This is it. You get the z-scores. Now, another, let's see an example of how we can, or how we do that practically. So random variable follows normal distribution with mean 10 and standard deviation 2.3. So now if you plot it, there are many tools available. You only need to specify what is the mean and what's the standard deviation of this data, and they're going to plot you the bell shape for your data. Now, what is the z-score for x is equal to 13? And for that, you just need to put values in that expression that we have just seen, which is x minus x bar over sigma. So x here is 13. This is the value for which we need to find out the z-score of, minus 10, which is mean, divided by 2.3, and we get 1.3. So for a value in your data set, which is 13, you get a corresponding value of 1.3 in the standard normal. Any distribution which might have any mean or any standard deviation can be converted into z-scores using this expression. And that is why we do not have to compute those complex functions and just look up the probabilities using the normal distribution tables. We'll be looking at what those normal distribution tables are and how to look up values from them. Now, another question, what is the z-score for x is equal to 9.1 for the same distribution? And we do this by 9.1 minus 10 divided by 2.3. And we get a negative value, of course, because we were dealing with a value which was lesser than the mean. Now, the z-scores typically vary from -3 to +3. And since we know that the standard deviation of a standard normal distribution is 1, 3 or -3 means actually 3 standard deviations from the mean. So that tells you another thing, which is that if your data is normally distributed, most of the values, majority of the values, almost very close to all of them will be within 3 standard deviations of the mean. And that can be is actually specified by this empirical rule, which we studied in one of the earlier lessons, which was 68, 90, which is also known as the 68, 95, and 99.7 rule. See this here. This is one standard deviation. And since we have a standard normal distribution here, we see these lines marked at -1 and 1 here, these central lines. And 68, the empirical rule says that 68%, which is more than 50% of the data, 68% of your data lies within one standard deviation, if it is a normal distribution. Then 95% of your data, 95% of your data, which leaves only 5% out of it. 95% of your data is within 2 standard deviations. And within 3 standard deviation, you have 99.7, almost entire of it, all of the data within 3 standard deviations. So this is the empirical rule. And this means that the probability of data falling outside 3 standard deviation is only 0.3%, or in probability terms, it is only 0.003. So you can already see that it is very low probability. And the farther you go away from the mean, the lesser the probability becomes.